Vanessa's reminded me why, as the Manager of Alumni Affairs here at Kaust, I love my job so much, because I just get to hear about the incredible work that the Kaust alumni community is doing all around the world. So thank you so much for sharing the information that you're gathering, and thank you so much for communicating it in such a passionate and, for those of us non-scientists, simplistic, and I mean that in the nicest possible of ways, way. So thank you again, Vanessa. Thank you. Now we have a wonderful last presenter. Hassan Al-Ismail is here to join us. And just a little bit of a plug about Hassan, but he'll talk more about himself. For those of you who have been at Kaust for a little bit of time, you would know about the Graduate Student Council. While Hassan was here, he served on that. And then once he graduated, he did a year on the Saudi Arabian alumni chapter. And I always like to put a plug in for the great volunteer or philanthropic work that our alumni and student community is doing. So over to you to talk a little bit more about your career.
Thank you, Leah, for the very nice introduction. Really appreciate it. Assalamu alaikum and good afternoon, everyone. It certainly feels great to be back here at Kaust. My name is Hassan Al-Ismail, and I did my master's degree in geophysics in 2014, and I graduated that year. And during my time at Kaust, when I was a graduate student, I was sponsored by Saudi Aramco. So when I finished my studies, I went back to work for the company. Now, when I sat down to prepare this presentation, I wondered what I should be talking about. I had a lot of things in mind. But then I asked myself, well, if I were a student attending the alumni lecture series today, what would I want the speakers to talk about? And my answer was, well, I would want them to talk about just a little bit about their career lives and their relevant life choices based on that. I probably would want them to talk a little bit about how their Kaust degrees worked out for them during their careers, and perhaps throw in some tips here and there about, from their perspective about their experience. So this is what I'll be attempting to do today in a very, hopefully, short presentation. So a little bit about my career. I work with the Near Surface Modeling Group in Saudi Aramco. And one question that may arise, because the Near Surface Modeling Group is part of the exploration admin area in Saudi Aramco, is, and I have been asked this a lot, is hydrocarbon exploration still relevant in the kingdom? Given the fact that both the kingdom and Saudi Aramco are undergoing a transformation. More specifically, one of the goals of Vision 2030 is to raise the share of non-oil exports in non-oil GDP from 16% to 50%. And another goal is also to raise the contribution of small and medium enterprises from 20% to 35% by year 2030. Now, in addition to that, Saudi Aramco is also undergoing a massive transformation, and this began in year 2011. And it's going from a simple, not a simple, but simply a Saudi oil and gas company to an international energy and chemicals company by year 2020. So we have two things here. Saudi Aramco and the kingdom are transforming, going into other things than oil. So it's talking about oil exploration still relevant. The short answer is yes, and this is for two main reasons, that Saudi Arabia is going into the non-oil businesses on top of the oil business. And also Saudi Aramco is transforming into an international company on top of its Saudi oil business. And I'm talking more specifically about the upstream business. So the title of my presentation is From Milliseconds to Oil and Gas. What do I mean by that? And I'd like to start by asking a question, and I just want to see by a show of hands, how many of you have seen a picture in the time dimension? Yeah, I know, it sounds a bit weird. Now I'm going to show you a picture in the time dimension. Simply, this is a picture in time or in the time dimension. But what does it mean? And how can we go from this picture to finding oil and gas fields? This is what I'll be talking about briefly. So the tectonic plates of the Earth are in continuous movement, and I feel in order to understand where we go from that picture to finding oil and gas, we need to get a good understanding of how oil fields form first. So the tectonic movements, in the right conditions, they could deform rocks in various ways. So one thing that could happen is that rocks could fold in this way. Rocks could break and form faults, normal faults in this case, or strike-slip faults. And this is a picture of the San Andreas Fault in California. You can see that the sidewalk is shifting a little bit. And we can see the effect actually year by year. So it's very noticeable. It could stretch and form ridges, or it could compress and form mountains, lots of things. So in certain parts of the world, with the right tectonic movement and the right rock types, we could have the right ingredients to form a petroleum system. So what does a petroleum system have? First of all, it has a source rock, a type of rock that's able to generate oil over the years and can sustain that generation. An example of a rock that could be a good source rock is shale, which you can notice from the color that it's rich in organic matter. But now, when oil generates from the source rock, it does not stay in the source rock. It migrates upwards, and it moves out of the rock through the pores inside the rock. And this is because of the huge pressure. And it continues moving until it reaches a non-porous rock, which stops it from moving. So the rock type in which it stays would be the reservoir rock. And a good example of a reservoir rock is limestone, which you can see it all over in Saudi Arabia. And why it's a good reservoir rock is that it has good porosity, so it has enough pore space within the rock in order to contain oil and gas. And also it has good permeability. So it's not enough to have good porosity, but also good permeability to allow oil and other fluids to flow inside the rock. So this is the second element of the petroleum system. The third element would be the rock that stops oil and gas from moving further, which would be the seal rock. And a good example of a seal rock is anhydrite, which you can guess that it has very low permeability and very low porosity, just to prevent oil from moving further. So that was the third element of the petroleum system. Last but not least is the anticline shape, the dome-shaped structure of the rock layer, which prevents oil from spilling outwards, because if it didn't exist, oil would just continue migrating to other parts of the subsurface. So once we have these four elements of the petroleum system, source, reservoir, seal, and trap, we could have the potential to have an oil field waiting for us to discover. But now the question is, how can we know where we should drill our oil rigs? Because oil fields probably exist, but we cannot know exactly where they are. And we cannot just go outside and drill oil rigs all over the place hoping to find an oil field, because that would cost us a fortune. Sometime in the past, this was done, but not anymore. In particular, if you want to drill a land oil rig or an onshore rig, it would cost about $15 million per rig. And that's the cheap kind. There is also the offshore rigs, which cost much, much more. So we need a way to guide us to finding the oil and gas structures. And the technique that we use is called seismic imaging. It's basically a way to image the subsurface in order for us to delineate structures that can contain oil and gas, like the anticline structure that you have seen earlier. So how do we acquire seismic data to do seismic imaging? Basically, if you look at this schematic example, if we wanted to acquire seismic data over this place in order to image the subsurface, which might look something like this, we would place a source for seismic waves, which in our case could be a vibro-sized truck, which could vibrate and send waves down to the subsurface. And also we would place receivers to gather those waves after they reflect from the subsurface. And our receivers in this case are geophones. So we just simply plant those geophones on the surface of the Earth. So once we shoot our source, seismic waves go down and reflect out of rock boundaries. And once we shoot the source, our receivers start listening in time, just like we're listening to sound waves in this room. And if we continue doing this for the rest of the area or along this 2D line, we would end up with seismic responses that if we put them together, they would form something like a picture in time, which would represent the shape of the structure that we have seen previously. So if the seismic interpreter looks at this picture, he or she can easily draw the structure of that structure that we were looking for. So easily they could connect these seismic events together and form this kind of structure. Now imagine the same example, but inserting a low velocity zone near the surface of the Earth. And by low velocity zone, I mean a type of rock in which seismic waves travel relatively slower. You can see that seismic responses in those areas of this line will not be affected because they don't go through the low velocity zone, whereas those that go through the low velocity zone will experience some time delay. So for example, this one and the rest will come a bit later than they should have. And you can see that the seismic interpreter will misinterpret this structure. And in real life, actually, this happens a lot. And it would, result in missing out on potential seismic or potential oil and gas fields. So how can we resolve this near-surface problem? This is what my team and I do on our daily basis. What we do is we model the velocity of the near surface. So we have, for example, tomography, full waveform inversion, uphole techniques. We use all of these things in order to model the velocity of the near surface. And once we have a depth velocity model, we can calculate the time correction that we can apply to the seismic traces in order to remove the effect of the near surface low velocities. This is equivalent to placing our sources and receivers on the datum of our choice instead of placing them on the surface. Thus, they wouldn't suffer from the effect of the low velocity zone. Now, of course, the interpreter would have a better time in picking the right events and connecting them together, resulting in the right structure in the end. So we do this on a daily basis. We receive seismic data, we calculate velocity models, then we calculate the time correction based on that, and we give it to the seismic processor, and then the interpreter would have a good time connecting the seismic events. And in Saudi Arabia, we're blessed with having very challenging near surface. For example, we have sand dunes. Imagine conducting a seismic experiment on top of the sand dunes and then having to remove the sand dunes from your data, or the effect of sand dunes from your data. We also have karst features or caves in the subsurface, which destroy our seismic signal and require a time correction sometimes in order to get the right structure. So all of these require that static correction in order to end up with the right subsurface structure. And now I'd like to talk a little bit about how the Kaost degree worked out for me. After I graduated in 2014, I would say that my degree worked out pretty well. I went back to work for the near surface modeling group, and I had the opportunity to apply what I learned here at Kaost in different courses at my work. I felt like I had a much deeper understanding of how our softwares worked, and a lot of the theory that went behind the methods that we apply. For example, I used what I learned in the numerical methods class, and I tried to write a code that would automate velocity interpretation in uphole depth-time relationships. And another example is I used what I learned in the geostatistics course, and developed, or let's say maybe proposed, a slightly different way of looking at how we spatially interpolate our uphold velocities. And I, of course, got to present these in local conferences. And before I talk about this, my boss was happy with the things that I contributed to the team, that he proposed to me that I should apply for something called the Specialist Development Program. And I was so excited about that. It's a program run by Saudi Aramco in which people who are enrolled, they spend 8 to 10 years developing their expertise in a certain specialty and usually getting their PhDs along the way, ending with being specialists in a certain field. So once he asked me to do that, I filled the application right away and sent it, but I had a little bit of a bad luck in that month. I was told that the Specialist Development Program was put on hold and they weren't accepting any new candidates until further notice. And until today, we're still waiting to see if they will accept more people or not. So I had a little bit of a bad luck at that time. But a few months later, I received another announcement in the email about something totally different. It was an invitation to apply for something called the Young Leaders Advisory Board in Saudi Aramco. This was a team that consisted of 16 people from all over the company who work on strategy-related issues and problems in the company. And usually the term for this team is about 18 months. So every 18 months, around 1,000 people apply for this program. 60 people get selected to join something called the YLab Academy. And out of the 60, 16 people make it to the final team of 16 members of YLab. So I said, well, if the Specialist Development Program was put on hold, maybe I should give this a shot. So I applied for this program, and thankfully I made it to the YLab Academy. And the YLab Academy, when I reached that point, I didn't know what I put myself into. It was literally the most stressful 3 days in my whole life. And I'm not exaggerating when I'm saying that. What they did to us, we were 60 people. They put us in 10 teams of 6 people. And they gave us a corporate challenge problem to work on. And they gave us less than 2 days to work on it. And we were expected to present our recommendations on the 3rd day. And I still remember the question that they asked us. It had to do with the job market of Saudi Arabia in 2030. And the question specifically was about what could Saudi Aramco do in order to help the kingdom create 5 million new jobs in 2030 by increasing the local content of the kingdom. And imagine we had to work on that for only less than 2 days and present reasonable, objective findings and recommendations on the 3rd day. It was a very interesting experience. Not a very nice one, to be honest. Imagine working with a team and having to work with a team, actually, when you're all competing for the same spot in the final. It was a bit kind of a conflict of interest, if you know what I'm saying. But long story short, thankfully I made it to the final team. And I'm mentioning this because this opened so many horizons to me. I feel like it was the best assignment that I have done in my whole career so far. After joining YLab, I got to work on so many projects that I didn't imagine I would have the opportunity to work on. Projects as small as improving the marketing plan for the thrift plan for the company, to as big as working on projects to propose ways to improve the productivity of human capital in the company by enhancing the employee engagement. And another example is proposing a new way to look at the work schedule of the company, and many other really interesting projects. Also, I got to communicate the corporate strategy to a lot of people, and that was one out of the many tasks that we had to do when we were in YLab. And I got to meet a lot of people. I got to engage with a lot of the youth of the company, especially. I also got to meet some very interesting, many famous people. For example, the CEO of EY, John Zimmer, the CEO of the company Lyft, which is competing with Uber and companies that do share economy and transportation. I also got to meet Daniel Yergin, and he asked me to take this picture with him. I'm not joking. Also our CEO and President, Mr. Amin Nasser. It was a very nice experience to work for that team. And when I finished working with YLab, I can say with total confidence that was actually the best assignment that I have done my whole career. It allowed me to work on projects that are far away from actually my specialty. It allowed me to see things from a big picture point of view, to look at things from a holistic point of view as well. So after I finished that, my boss came to my office again and said, well, you might be also good at doing other things, so why don't you pursue an MBA? So he nominated my name to pursue an MBA with HKUST, the university from which our new president comes. And I started that a year and a half ago. So hopefully, inshallah, by mid this year, I'll be done with this degree. Now, if I look back at the few years that I spent after I graduated from Kaust and try to summarize what lessons I learned, I would say the following. First of all, time matters. It might be only a few milliseconds, but missing those few milliseconds will probably make you lose a oil or gas field. So time matters. There are always problems in our lives, in our career lives, and other things, but there are always opportunities, and it is our job to look for those opportunities and pursue those opportunities. Last but not least, it might not always be beneficial to look at the big picture, but it never hurts to see things from that point of view. Thank you.